Hey, Caden and Zoe right there. What questions do we have? We have some stuff from last office hours that we didn't get to. So what should we do? We'll put a little music right here, get started. Len got a little snack. Sorry for the delay in start. But if you're here in the chat, let's wake up Mewbot. Jackson, good to see you. What should we work? Oh, Mewbot was awake and I put him back to sleep. What should we work on here? What should we do? Let me know. What should we work on right here? What should we work on? What are people's thoughts? What should we work on? You tell me. You'll start working on it. Oh, there we go. Chapter 5. What do you want to work on Chapter 5? What should we work on Chapter 5? Yeah, well, just let me know. What? Good to see you here, Lachey, too. What should we work on? You tell me. We start working on it. Name the problems. Name the thing. Chapter 5 is the tough one. Great job starting it right now. Let's throw 1,000 points for everyone starting up some Chapter 5. Homework question 2. Okay. 1,000 points for being here. This is Chapter 5, Part 1, Homework 2. Access denied. What? Ma Pearson. Let's check it out. Can we redo the running one? The running one on the Canvas content? The running one on the Canvas content? Assignment manager. Assignments open up. It's taking its time to open. When is our first exam? People were dropping the chats on the syllabus. So check out the syllabus, and the syllabus has the first exam date. These questions right here, you can only get them down if you practice them. So make sure to be practicing these. Oh my gosh, my Pearson's acting so crazy right now. It was from lecture. We could do that one. So we've got question 2 on Chapter 5, Part 1 homework. Okay, let's go check that out. Question 2, Chapter 5 homework. Okay, let's take a look right here. And then we'll do the running problem next. Stat 201, Chapter 5, Part 1, homework, question 2. And then we have Stat 201, Chapter 5, running example question. Okay, so here we go in just a second. And let's take a look at Chapter 5, question 2. Here at 5:13. Let's do it. Okay, so this question right here says that people with a z-score of 2.75 are sometimes classified as geniuses. If the aptitude test has a mean of 100 and a standard deviation of 12, what score would someone need to be classified as a genius? So what does a z-score tell us? Let's look at the formula for the z-score and remember how a z-score formula works. What does the z-score formula tell us? Let's look at it. A z-score is going to be this. We have observation, which is what somebody is. That is somebody's IQ right there. Minus the mean, which is the average IQ score, divided by the standard deviation. So the top part of this equation is just somebody's what? The top part of that equation, this is like somebody's IQ minus the mean, is just how far somebody is what? Your IQ is 128 and the mean is 100. What would that solve for? Is like an example, like you have an IQ of 128, the mean is 100. So I do have a mean 100, right? What would that tell us? So the important thing here is to understand what the formula is telling us. So you have an IQ of 128. That's what Y is, your observation. The mean of the distribution is 100. What does that tell you? Does anyone know? We got to figure this out. What does that tell us right here? Just think about what it means to say, like, just talking about that highlighted box right there. What does this mean? The first part of this is somebody's what from the mean. If you subtract two numbers, you're getting their what? So when you subtract two numbers, you're just finding the numbers what's. Z-scores are super important in statistics because we're finding the what between these two numbers. So what are we finding right here? We're finding the what between two values. We're finding the what between two values. We're just finding the two numbers what's. Does anyone know? Let's see. Go it a little longer. That's the what between the two numbers. Points on the line right here. Not standard deviation, so that's not... Well, think if you subtract two numbers, good answer right there, Shay. If you subtract two numbers, you're just taking their starts with a D. If you subtract two numbers, you're just finding their what? Their difference. We're just finding... Does that make sense? Good answers right there. We're just finding their difference. So that's the difference between you and the mean. Does that make sense? Just this first part right here, observation 128, mean 100. And then the bottom part of it is where we take the difference and we standardize it. So this is going to be the standardization of this difference. Now, if this was the distribution right here, what would be your z-score? What would be your z-score? What would be your z-score here? So solve the mathematics. This would say that IQs have a mean of 100 with a standard deviation of 14. You scored a 128. What is your z-score? Because it's not about solving this one problem. It's knowing how to solve any problem that gives you these numbers. It'd be 2. Great job, Lachey, right there. It'd be 2. We press all the points buttons right there. So if somebody told you that their z-score was 1, what would be their IQ? If somebody said my z-score is 1, what would be their IQ? So try to think about what it means to have a z-score of 1. Z-scores tell us how many standard deviations something is above or below the mean. So what would it mean to have a z-score of 1? Because a z-score tells you how many standard deviations something is above or below the mean. So if somebody had a z-score of 1, then they'd be 1 standard deviation above the mean. So what would their IQ be? So if somebody has a z-score of 1, they'd be 1 standard deviation above the mean. So what would their IQ be? If you had a z-score of 1, the mean is 100. You're 1 standard deviation above the mean. So if somebody had a z-score of 1, what would their IQ be? What would their IQ be? If you had a z-score of 1, what would your IQ be? So it would mean you're 1 standard deviation above the mean. So what would your IQ be? If you had a z-score of 1, what would your IQ be? 114, Lachey, great job right there. Because you're 1 standard deviation above the mean. Yep. So you're 1 standard deviation above the mean. So think about this. Let's use our numbers from this problem to solve a similar question. Mouse, don't act weird now. So let's do a similar, or let's solve our problem here. It says mean of 100, standard deviation of 12, z-score of 2.5. So we know the z-score right here is equal to 2.5, or 2.75, excuse me. And we know the mean of the curve is 100 and a standard deviation of 12. So now, don't tell me the answer, but think where the answer should be if we're looking for a z-score right here. Don't tell me the exact answer, but give me a guess of the answer. So the z-score of 2.75 is about there. So somebody's IQ should be between what and what? Like, what should their IQ be between? If their z-score is 2.75, then the answer for their IQ must be between what and what? And always do this. 124, great job, Lachey, right there. So then how would we figure this out? We have to figure out what 2.75 standard deviations is. 2.75 times the standard deviation is going to tell us how far they are above the mean. So this value right here is how far they are above the mean. It could be below if it's negative. So if I solve this out, I get, that should be 3, so that should be 9. I should get, is it 33? So this value right here is 33. So what is the answer to this question? If the value is 33, then what is the answer? And think about visually speaking. Visually speaking, what is the answer? So they're 33 units above the mean because they're 2.75 standard deviations above the mean. A standard deviation is 12. So what is the answer? see what the answer is. Give it a moment longer, see if people can figure it out. Because we can go and solve this backwards now. I'll write the answer formula up here. We want the observation. The observation is equal to the mean plus the z-score times the standard deviation. So we know what the mean is. The mean is 100. We know what the z-score is. The z-score we said is 2.75. We know what the standard deviation is. The standard deviation is 12. So we can solve that formula. So what's the answer? So we just need to plug everything into this and solve. Or we can understand that it's 2.75 standard deviations above the mean. So what would the answer be? If you don't know is a fine answer too. But always drawing it out can really help. The answer is kind of drawn right here for us, because that's what we're doing right here in the formula is we're adding to the mean that many standard deviations. So Jackson, think about this. We know the answer if we go to the mean and go up this much. This is where the answer is at. The answer is right here. So this is the units of the problem now. And so the mean, so the first part of this is the mean. Let's highlight that. The mean is this. That's the mean. And then the plus we are adding to it is this component right here. This is what we're adding right here. 133, yeah. Are you starting to see it a little bit more? That's the mean plus 2.75 standard deviations. So hopefully drawing it out can hopefully help, and practicing it, the answer is 133. So how do I keep making the mouse slower? I don't know how. It's magic. 133. And that should do it right there. But remember, practice this, draw it. It takes a little bit of practice. We've been doing a lot of these problems today, but drawing it out can really help, and knowing how to use the formulas and understanding what a z-score is a huge help. Let's do one more of these. People said question number 4, which might be similar. So let's do question number 4, which we haven't done yet. Then we're going to do the running problem again. Okay, so this one, ooh, this is a fun one. Let's take a look at this one. So this is question 4 on the homework, and let's put the timestamp here. This is going to be at 14 minutes, 43 seconds. So this one says a company's customer service hotline handles many calls and gives refunds and all that good jazz. So in length of calls, the hotline is 5.71 minutes. That's the median with an IQR of 2.5. If the company were to describe the duration of these calls in seconds instead of minutes, what would the median and IQR be? Okay, so think about this. We have to take the median and IQR and do what? If we were to turn these into seconds, we would have to take both values and do what? So we want to turn these into seconds. So what would we do to these values right here? To turn 5.1 into seconds and 2.5 into seconds, we'd have to do what? How would we turn those into seconds? So this is 5.1 minutes. What is 5.1 minutes, and how would we solve that? How would we get 5.1 minutes into seconds? So what would be the median if it was not 5.1 minutes, but seconds instead? How would we turn minutes into seconds? Not close answer, good answer, Jackson. Not divide. That's how you turn seconds into minutes. We want to turn minutes, so not divide. We want to turn minutes into seconds. So with this right here, the median call lasted 306 seconds. The IQR, which is the range of the middle 50%, lasted, and this should be 150. Does that make sense right there? So now we've just changed it. Multiply, great job, Kayla, right there. So that's a shifting and scaling. That's the idea of shifting and scaling, which we've talked about with turning things into z-scores. Shifting and scaling doesn't change the shape of the distribution. It just changes where the center of it's at and the spread, but like still the same data. It's changing just the way it looks to a different kind of set of values. So we've shifted and scaled it to seconds. We should probably z-score it instead. In effect, to speed up the customer service process, the company will decide to streamline the series of push-button menus customers must navigate, cutting the time by 18 seconds. What will be the median and IQR? Now, this one's interesting because they're making the calls faster. So what they're changing is they're changing either the center or the spread. So if they make the calls faster, I want to show you what the distribution looks like and why this is a great question. We currently have the mean right here at 306 seconds with the IQR, which looks something like this. What was it? 150. So if they were to make the calls faster, that would shift the what. And it says mean, but we could use mean or median. It says mean, excuse me. If they were to make the calls faster, that would change the what of the distribution. If you were to make the calls faster. So let's draw like a new distribution down here, but on the same number line of sorts. If you were to make the calls faster, that would change the what of the distribution. If you were to make the calls faster, and said by what, how many seconds? 18 seconds. If you were to make the calls faster, not the spread, good guess right there. So it'd make the calls faster. If we make them faster, it would change the center. So making them faster shifts it over to a faster time, but we didn't change the spread of the distribution. Does that make sense? It still has the same spread, but the mean or median, it's using median right here. But if you were to shift it and say things are now faster, but the variation is still the same, the spread right there, which is the IQR, is measuring a kind of spread of the distribution, how far away those values are. And that hasn't changed. It's just that things are faster. So there's still the same amount of variation, the same spread in the data. I copied the distributions. But now it's a little bit faster by 18 seconds. So that would make the median, they keep using median for this problem. It'd make the median lower, but the IQR would not change because IQR is a measure of spread. So it's important to understand right here, it's talking about what would change here in this problem. That's a good problem. I like that one a lot. So maybe we'll finish off the homework, then we'll do the other questions. Jackson, thank you for asking. Let's finish off the homework right here because we have some multiple choice, but it's important to be able to guess the multiple choice or to know it before you click the problem. So before clicking the answers, got to click the problem. So Stat 201, Chapter 5, Part 1, Homework Q5. So with this right here, the fifth question, shifting data by adding a constant to data values does not change the what. So think about this. If you were the average score on the test, then if I gave everybody 20 points, would the average increase? If you got the average grade on the test and I gave everyone 20 points, would the average score increase? Yes or no? If I gave everyone 20 points on the test. So we have here test scores. There's 3 students. And we go right here and we got student 1 made a 60, student 2 made an 80, and student 3 made 100. Yes, it would change because the average right now is what? So let's compute the average for this. The average right now is what? Just tell me the average of that data. What is the average of that data set? It's symmetric. It's 80, right? So we got here y bar equals 80. How about if we give everyone 20 points and then we have right here 80, 100, 120. So what would be the average of the new data? Great job, everyone. What would be the average of the new data? So this is old and this is new. What would be the average of the new data? It'd be 100. Yep. So this is y bar of new down here equals 100. So the mean changed. What about the median? What is the median of the top? What is the median of the bottom? What is the median of the top distribution? What's the median of the bottom? I made this easy by using 3 numbers. And this is a symmetric distribution. Great job, Lashane. Great job, Kayla. Excellent. I'll throw 1,000 points. Thank you for everyone following along and doing this right here. 80 on top on 80 on bottom. Why do you think mean and median kind of did the same thing right here? Because they're both measures of what? The mean and the median are both measures of what? Which we changed right here. They're both measures of what? They're both measures of center. So the center definitely changed when we added a constant. But let's look at this value right here. Let's look at this, and I'm trying to tell you to find the what right here. So what do you think I'm highlighting in green right there? I'm trying to tell you, maybe let's look at the what of the data. Let's look at the what of the data. The range, great job, Jackson. So the range in both of these is equal to 40. And also the IQR would be the same. It's going to probably be like 20 or something like that. So let's put 20. It's just an estimate. I could put it into R to find the exact answer. Why not? Here, watch this. Go down here, go to R, say IQR, concatenate. It's 20. There we go. Confirmed. That's why it's like you don't have to figure these things out by hand. You can just get all the quantiles pretty quickly if you just go quantiles and then run the code, and there's the answer. So there it is. There's the data set. There's the answers. And that's why it's like I don't like finding Q1, Q3 by hand. It's just like you can ask. The computer will tell you. So you just have to know what it is and why it's important to understand. So notice this, that the spread of the data remained the same. So what we've learned right here is that adding a constant changes the center. Adding a constant does not change the spread. Braden, good to see you here. So by adding a constant, it does not change the what. So which of these right here should be good? Adding a constant to the data value does not change the what. Which of these sounds like a measure of spread right here? Which of these sounds like a measure of spread? The standard deviation. Now, you might think the quartiles, but IQR is a measure of spread. The quartiles are positions, just like the median is a quartile. Median is Q2. So Q1 and Q3 would change. I can show you that here with the data by using the original data set and the new data set. So that's the new one. And the original data set we made look like this. So here's the original data set. We'll do them both in tandem. So here's the quartiles now, and you notice the IQR has not changed. It's still a distance of 20, but the quartiles have changed. So the standard deviation, watch this, standard deviation, boom, boom. There we go, confirmed. Standard deviation has not changed, confirming just with our little data set right there that the standard deviation did not change. A lot of good stuff. And if you can see, that's why I really love using code right here, because you can just ask, what is the median? And it'll just tell you the median. You say, what's the mean? It'll say, oh, there's the mean. Just changing the code. So nice, so neat. You can run it like that. I love code, love code. Ooh, let's finish off the homework right here, because I think this might help with some of those questions, Jackson. So we're going to finish off the homework right here, and then we'll do, but drop more questions, because I know people are wondering about chapter 5. That seems to be the questions. Who wants to finish off the homework? Does anyone like, let's finish off the homework right here? Who would like that in the chat? Be like, let's do the homework. Let's finish it off. Stat 201, chapter 5, part 1, homework. Oh, we just did question 5, Q6. Jackson saying yes right there. Me says Lachey right there. Awesome. So with this question right here, we have the normal model, and we're using the empirical rule, the 68, 95, 99.7 rule. We see right here that it's normally distributed with a mean of 100 and a standard deviation of 17. So when we draw out the curve, what goes in the center? Just four-letter word. What goes in the center every time we draw the curve? Drawing the curve, every time, we should put the what in the center. So we can help narrow down the choices pretty quickly on this by looking here and saying, oh, if I draw the curve, which you should also do yourself, we could do that real quick. 117 are the numbers. So you want to try drawing it. The average, great job, Lachey, right there. This is the practice you want to try to do, is if you get something normally distributed, oh my gosh, normally distributed with a mean of 100, standard deviation of 17, you want to try going here and drawing your curve. Sometimes we have cheating in class where when we give in-class quizzes, we give people different means and standard deviations for their curves, and then someone will have the numbers from someone else's quiz, because we'll have like 4 versions. And it'll be like, why did you write down 120 for your mean? And they'll be like, oh, I got confused. And it's like, your thing says 140, but you use the mean standard deviation from a different version. Or it's like, oh, I don't know. And you're like, your numbers are from a different version of the quiz that we passed around. Were you looking at someone else's thing? Just, I can't. This is the distance we go up right here. I hate dealing with it. I hate it. It's just like, I wish someone would say, yes, I looked over at another person's quiz. I'd say, oh, that's really bad. It's like, ay. So, yeah. So this right here is when we draw out 3 standard deviations up and 3 standard deviations down. So I'm trying to do this from the top of my head, 66 and 9 right there. There we go. So there we go. And looks like 49's there. 151. Uh-oh. So now we have to figure this out based on the empirical rule numbers. Inside of -1 and +1 is what percent of the data? Inside of -1 and +1 is what percent of the data? So we just drew out every number they put on the curve ourselves. But inside of -1 and +1 is what percent of the data? This is where you have to know the empirical rule. Inside of -1 and +1 is what percent of the data? So inside of -1 and +1 is what percent of the data? 68. Great job, Jackson, right there. 68. So we've done that correctly. Boom, right there. We got it. So we have the right numbers on the curve, and then we have this. Now, Jackson, this is what you were asking about by doing the questions. And great job, Lachey and Kayla right there. Keep those answers coming. Keep practicing. These are things we have to know very quickly. I know the problems show it, but we also have to memorize it and be like, okay, 68, 95, 99.7 are the percentages of values within 1, 2, and 3 standard deviations, respectively. So now it says, in what interval would you expect the central 68% of scores to be found? So we have to look where. So the central 68 are plus or minus 1 standard deviation. So the central 68 would be what? And this is something we could draw. The central 68 would be what? The central 68 would be found between where and where. So use this information to say, for this IQ test, the middle 68% of scores would be between what and what? So you're looking at the middle 68, which is plus or minus 1 standard deviation. So the middle 68 is plus or minus 1, so minus or plus 1 standard deviation. Great job, Kayla, right there. Excellent work. Kayla, shout outs. Keep up the great work. Good studying, good reviewing. We're throwing out those points all the time because it's a big way to the top of the point leaderboard. So we have here 83 and 117. Check answers right now. I do want to point out, you might say, well, how could I do this without the pictures? We can draw the exact same thing over here ourselves by doing the 68, 95. This is where you become a pro if you draw it out and put your own numbers here and try to draw it out with each problem. This is where you get the real practice. So grab a sheet of paper and try to do it by drawing it out. About what percent of people should have IQs above 151? Now, if you look, 151 has a z-score of what? 151 has a z-score of what? So just very quickly, just look at what we drew, which means it's 1, 2, 3 above the mean. That's the answer. It has a z-score of what? $151 has a z-score of what? What is the z-score of it? 3 standards from the mean. Great job, Kayla. So with this, what percent of area is between 151 and 49? Now, I know it didn't ask about 49, but here's where we have to use our knowledge to say between 151 and 49 is what percent of area? Remember, we're using our drawing right now to practice. Between it is 99.7. So let's subtract this from 100 to get the area outside of it. Now, the area outside of it would look like the following. It looked like this and like this. We don't want all that area. We just want this area. So what should I do? Because this looks like twice as much as I want. I don't want both of these. So that's what the equation's finding up top of the screen there. I just want not all of it. I just want not double. What should I do? Since it's symmetric, I just want one of those. I just want to do what? What should I do? Because that's the outside area. 99.7 is inside, 0.3 is outside. So I should take my outside area and do what to it? Because it's twice as much as I want. I don't want this and this. I just want this. Or a mirrored this and this. I just want this. Divide by 2, exactly. Great job right there. So let's divide it by 2. And when we divide it by 2, that's the area on the top side. Divide by 2, just it's half of that area. Because right now we have this and this, but we just want this. And the reason we divide by 2 is due to the symmetry of it. So since it's symmetric, we can just say, well, above that, we know 99.7 is inside, 0.3 outside, half of that is 0.15. So 0.15 as a percent right there. This one right here says between 49 and 66. Now, this is a tougher one. Let's take a look at the tough one right here. 49 and 66 are z-scores. Remember how we just found out that this is 0.15 right there? What is the z-score of the values I'm looking at? The values we are looking at are here and here. What are the z-scores of this? This is a tougher one. What is the z-scores? Not this part, but just think of the highlighted numbers I'm showing you on the screen. What are the z-scores of those? The two highlighted numbers have z-scores of what and what? -2, -3, exactly. So we want the area between here. And remember, we just found, so we want this area right here. And we just found this area. Let me ask you this. What percent of area is below here? What is that orange arrow worth? So that orange arrow is how much area? Hint, use this right here. How much is that orange arrow worth? Which is not the answer. 2.5. Great job. That is correct for the orange arrow. But the orange arrow would cover everything below here. So what do you think we'd have to do to find the answer here? Because we don't want everything. We don't want this. So what do you think we should do here? If we know that the small area is 0.15 and the big area is 2.5, how would we get this? How would we solve this answer? Great job, Kayla, right there. Yep, and that's one of the toughest ones. These are what I would consider the toughest empirical rule questions. Now, what you can memorize, I'm going to write these on the screen right here. You can memorize them if you want. The answers to the area or below this is 0.15, 2.35, 13.5, 34, 34, 13.5, 2.35, and 0.15. Let me grab a better picture of this in a moment. But what's the easiest way to know that each one of those is 34? Like, just think theoretically, what's the easiest way to know that those are 34 right there? Like, between 83 and 100 is 34% of the area. You might be able to see it really quickly. That's an easy one to get right there. Like, if you think what's going on here with this up here and how you can easily get that those are each 34%. And I'm going to grab a better picture because there's a really good picture of this online where you don't have to read my handwriting. How would you figure out that those are worth 34 right there? Divide it by 2, exactly. So divide that. Let me grab the really good picture of this, and I'll probably be showing this starting next class. Great job, Lachey, too. 100 points, everybody. So, empirical rule, 68.95. Someone put a really good picture of this. I thought we put it in the slides lately, but it breaks down all the numbers. Here it is. Okay, copy image address. Copy image. It's a much better drawing than I can do. There we go. Okay, so here this is a good curve to have. Take a picture of this. But with this curve right here, we could just put in our numbers. And you could see right here with inputting our numbers, which I think was 100, and then 83, and then 66, and 49. If you use this, or you can write this out, it makes every one of these problems way, way easier. Because now all you have to do is say, I'm interested in the area here to here. And there's the answer of 2.5. Does that make sense, Kayla and Lachey right there? Like, now I can just see the answer visually. It's between 49 and 66 is 2.35. I can also see above, for the previous problem we just did, above 151, there's the answer of 0.15 right there. It makes it way, but you want to be able to draw this out. This is why I pulled up the graphic to make it easier for you to see rather than you reading my handwriting, because I've memorized those numbers, 0.15, 2.35, 13.5, 34, 34, 13.5, 2.35, 0.15. One way to get these correct is to know that they're symmetric. And also, if you're adding up your numbers when you get to the middle, you should have added up to what percent. If you're doing this and trying to write this on the test, because you can, I tell people, start by drawing out a normal curve on the test to help yourself out. If you're adding up these values to the middle, what should you get? If you add up these values right here to the middle, like if you add up this, 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 at the middle, you should have what? By the middle, you should have what percent? Not 100. Good ass right there, Slade. 100 by the end. But by the middle, good ass Lachey right there. 50%. Yep. So this would be the 50th percentile right here. So you can see right here, this is the 16th percentile. This is the 2.5th percentile. And this is the 0.15 percentile. This is the 84th percentile. This is the 97.5th percentile. And this is the 99.7 percentile. And there are 97 point, ooh, almost made a mistake, 99.85th percentile. So using this information right here, I can also write the percentiles on the curve because it's just how much of the curve have you gone through. Does that make sense? What I'm doing, this is 0.15. I add to it 2.35. I add to it 13.5. Remember how there's 16% below there. I add to it 34. I get 50. I add to it 34 again. I get 84. I add to it 13.5. I get 97.5. I add to it 2.35. I get 99.85. So this can be a huge help when you're doing percentiles, but this right here is good knowledge to have. I'm probably going to use another graphic. We have two next class to start out, but try drawing this out. Because now when we get to the next problem, watch how much easier it is. Okay, so this was between here. So this is, how do I keep doing this? Keep changing my mouse speed. So right here above 134. 134 has a z-score of 2. Since 134 has a z-score of 2, I instantaneously know the answer to this is 2.5. Let's see what I have right here. Because of the drawing, you can see right here, 134 is right there. And all I would do is add together those values. Is that making sense, Kayla? Because I know where 134 is at a z-score of 2. I can just add together those values to get the area on the curve over here to the right. Also, we know 95 in the center. An alternative solve, which is great to do also, is to say 95 in the center. With 95 in the center, it leaves 5% total outside. With 5% total outside, it'd be 2.5 either side. Knowing how to solve this two ways is going to be a really good way to double check your answers. Breaking it down by parts or using the empirical rule as is, but this is really good practice on using the empirical rule, which are some of the questions. Which of the following is a true statement about z-scores? I think it's going to be all of them. Z-scores standardized data, very true. Z-scores have a mean of 0, great job, Kayla. A mean of 0 in standard deviation 1. A z-score is a measure of how extreme a data value is. Yep. A z-score tells us how many standard deviations of value is above or below mean. That is the direct definition. So all those answers are very true. Things you should know. Right here, the first question, since she scored, let's see right here. This is the economics, I believe, 83 and 72 and 9. So that is 1.111 above the mean in economics. And the math is 87, 65, and 10. So that's 1.2. She did barely better in math. Check out the ones earlier where we went over this more in depth. Oh, no! The economics, she scored an 83, 72, and 9. Wait a minute. No, wait. 83 minus 72 divided by 9, 1.2. Oh my gosh. Is she better in economics? Oh my gosh. Don't do the problems quickly like Brian. Don't be like Brian. 80. Wait. Check it out. She scored an 87 in mathematics. The mean was 65. So what's her z-score? I'm just showing you what happens when you try to do the problems too quickly. She's 22 points above the mean in math. She scored an 87 with a mean of 65. So what's her z-score? Not 1.2. The standard deviation is 10. So what's her z-score? You go too quick, you get problems wrong. What's her z-score? She's 22 points above the mean. The standard deviation is 10. What's her z-score? Chapter 5, a high school users using information about February. Oh, cool. Yeah, quiz. Let's do that. We'll do the quiz here. Content quiz, yeah. Contingency table, yeah. We'll do that here. We got the Canvas content. We'll do that here, and then we'll do the quiz question, then we'll do the Canvas content. So what's her z-score, though? She's 22 points above the mean, and the standard deviation is 10. She's 22 points above, and her standard deviation is 10. So she's 22 above, standard deviation is 10. So we have that she scored an 87. The mean was 65, right? So what's her z-score? What is her z-score? Her z-score is what? She's 22 points above the mean, and the standard deviation is 10. So she's 2.2. So she did better in math. It's my last try. Woo! Don't do a problem quick like Brian, you'll get it wrong. -2, so 69. There we go. You get some extra tries at the homework. I just like to show you get extra tries. Every once in a while I get something wrong. Let's do the Chapter 5 Part 1 quiz with the temperatures in February. And then we're going to do the Canvas content. So let's see right here. Let's do the temperatures. Go back to the main screen. Okay, we're going to do some Stat 201 temperatures in February. Stat 201. Chapter 5 quiz. Part 1 temperature data. Okay, let's go check this out. Temperature data. Close out that. Chapter 5, Part 1 quiz. Okay. Muskin, good to see you here. We're going to do the Canvas content next after this. And let's find that February question. Here we go. Here we go with the temperature question. 43. Here we go. Wait. A high schooler uses internet to get information about February. No, a high schooler, where are they? Where is the high schooler working on the homework? Can you go over the quiz? Tell me what the quiz says, because the quiz is different. Ivana, good to see you here. The quiz is different for each person. Here we go, right here. We found it. Okay. So a high schooler uses a high school senior. Quiz is different for each person. So tell me what your question says. A high school senior. Okay, yep, this one right here. And let's timestamp this. 44. 33. Okay, here we go. A high school senior uses the internet to get information on February temperatures in the town where he'll be going to college. He finds a website for you with some statistics, but they are given in Celsius. How dare they? The conversion formula is as follows. Determine the Fahrenheit equivalents for the following information below. So if you look, it looks like they're giving a lot of the 5-number summary to start, or the maximum temperature. That's the highest temperature. Whoa. The maximum? The mean is there, and the range is there. The median is there. Do they actually want you to find out the min? That'd be interesting, because you could figure out the min from this, because if that's the max, you can figure out the min. So this is a bunch of conversion right here. Oh my gosh. Okay. So I'm going to show how to do these, and it's just asking us to convert all 6 values, right? Okay, so this is just how it's the goal of this problem right here. It's a very mathy problem. The goal of this problem is to show you that you can change data without changing not change the context. You can rescale data. You can take data and shift and scale it over to another distribution. So this is on a Celsius distribution, and we want to bring it to a Fahrenheit distribution. So what you have to do right here, and you want to make sure the temperatures make sense, is you want to take a temperature right here like maximum temperature. You see how max is the first one right there? So the maximum temperature is 12. So you want to plug it in right there. Let's show what this looks like visually. We're going to solve one of these, and I'm going to use R to solve the remainder. You want to take right here and plug 12 right there. So the first thing we'd do is we'd multiply these values and then add 32. Add 32. Does that make sense? So you're going to go 9/5, or 9 times 12, divide by 5, plus 32. And then you can also, watch this. You want to see something cool, Sarah? What is 12 degrees Celsius to Fahrenheit?
That would be 53.6 degrees Fahrenheit.
53.6. What is 2 degrees Celsius to Fahrenheit?
The answer is 35.6 degrees Fahrenheit.
What is 4 degrees Celsius to Fahrenheit?
The answer is 39.2 degrees Fahrenheit.
I love the digital age. What is 31 degrees Celsius to Fahrenheit?
The answer is 87.8 degrees Fahrenheit.
That's right, right? Yeah, it's going to be... That's a large range of values. Let me see, because there might be a trick to this. I'm a little worried about that one. It's a big range. I guess the temperatures do range that much. That's the maximum? Let's go to... Except for range, standard deviation, IQR. Yeah, that's where I'm a little wondering about this. So... There's a trick to it. Yeah, that's what I'm thinking. That's where I started to think over this. I'm starting to think about it right here. So, oh, I know what it is. I know what it is. I know what it is. So this is the trick. Because that's where my brain said wait. Because I want us to think about this. If this is the maximum temperature right here, does that make sense? That's the maximum temperature. The maximum temperature right here, we need to figure out, this is where the trick comes into play. We need to figure out what the minimum temperature is. How can we figure out the minimum temperature right here? How can we figure out the minimum temperature? So if I know the max and I know the range, how could I figure out the min? How could I figure out the minimum temperature? So I want to figure out the minimum temperature in Celsius. How could I figure out the minimum temperature in Celsius? Subtract the range from the max, exactly. So this means 12 minus 31, negative 19. Gosh, it's going to be cold, right? So what is negative 19 Celsius to Fahrenheit?
Minus 2.2 degrees Fahrenheit.
Minus 2.2. Okay, that's the big thing. That's the solve right there. So the min is 2.2 Fahrenheit. Does that make sense? And does that make sense how I found that? What I did is we found the min in Celsius. So we did max minus range equals min. And now we know the min in Fahrenheit. We do know currently the max in Fahrenheit. And the max, and that was negative 2.2. Okay, I got to make sure this negative is clear. Okay. It's got to be negatives, doesn't it? So now we go here and we say the max is 35.6. 53.6. How did I say 35.6? 53.6. Okay. So what would be the range of this data now? So use this information now. We should have the right range, I believe. It's an interesting, very mathy type problem. We love math problems here. What will be the range of this data now? Take a moment and see if you can find it, because this should be the correct range now. Close, Sarah, close. Think about this. If you go through 0, you have, yep, Kayla right there, yep. And great job, both of you. 500 points. Keep it up. Don't worry about getting things wrong here. We love the practice. If you think about it as a number scale, it might make sense because you're going through 0. So the range of the data values, if you go through 0, like this is 53.6. And if you're down here at negative 2.2, then you've gone through 0. So the range is going to be longer. No, Sarah, don't worry. Shout outs to you right there. A lot of people just, how do I keep changing the mouse speed? I am worried something is wrong here. I hit it like 10 times today. With this right here, the range would be that. So it'd be 55.8. And so that one, tricky one right there. So that is the range. And you were saying it said you were wrong on the, I got everything right except range, standard deviation, and IQR. Okay. So IQR is also based on positions. And so to know the IQR, there's the IQR right there. So when we think about the IQR, we should be able to, we need to know the positions. The median is 4 degrees Celsius. The standard deviation, you had a standard deviation of 5 degrees Celsius. So it said you were wrong on all 3 of those? Oof is a new question. Man, I would never put this as a test question. Gives us the max. Let's draw what we have. Right now we know the max. Question's making me think. What's it doing making me think here? Okay. So if we know the max, we know the min. These are values we know right now. We know the range. We know the median. We know the IQR previously. We know the IQR in other units. And we know the standard deviation in other units. Just want to do the range divided by 6. Let me see if it has any other information. He finds a website, but they're given Celsius. Determine the equivalent Fahrenheit. So the problem is we're not converting. We're not converting, like 18 degrees is a measure of spread, is not the standard deviation. Yeah. So the issue is when you're taking 18 degrees, you're not converting, and I don't know if they want us to assume this is a symmetric distribution or, man, they could go rather interesting on this. So the standard deviation is a measure of spread also. So you said, I told you were wrong on the which ones again? Let me double check. Range, standard deviation, IQR. So the standard deviation is oftentimes 1/6 of the range if they want you to solve that way. Like 1/6 is a good estimate of it. And we know the min and the max. What did we get for min and max? Min is negative 2.2, and the range is 55.8. So we know that. I don't like this question. It's more about just math solvy stuff. We've never written a test question like this. Tell Terry. It's a bad question. This is an estimate of the standard deviation right here. Standard deviation should be something close to 9.3. Should be about 9.3. Knowing that, I can get us, this is like, I would not expect you to do these sorts of solves. I might even look to see what they say to solve it. So that's kind of our estimate of standard deviation. Dividing the range by 6 gets you an estimate of the standard deviation. And I'm using the Fahrenheit units over here. And then also I know that the IQR has a consistent z-score. So now that I know the standard deviation of the IQR is between negative 0.674 to 0.674, which is going to be this. I'm wondering what solve they use. And so if we times that, 0. Something is weird with my mouse. And then times that by this, 0.674 times 2 times 9.3, 12.53. Somehow the numbers are actually the same on your version. Mine says the standard deviation is 12.6. 12.6 for the standard deviation. Okay, let's see how to solve that. Thank you so much, Sarah, for being here as we work this problem. So let me think about what they give us, because this is quite the riddle right here. 500 points, Sarah. So standard deviation, dividing the range by, no way would they do that. Let me see right here. We got a range of 55.6, right? So they're saying it's 12.6. Okay, so that's a lot smaller. Standard deviation is 5 degrees Celsius. So, oh, wait a minute. Okay, I think I know how to solve this. Okay, I think Sarah, I got how to solve this. Man, this is tricky. Okay, I know how to solve it. You ready? Oh, gosh. Oh, well, okay, here's what we should have done. Man, this is good. I see the solve now. Okay. So what do you think we should do to this data now? So we know that this is what the Celsius curve looks like, right? It's not as bad as I thought. We know what the Celsius curve looks like now. So what should we do? The next one is very, very tough. We know what the Celsius curve looks like now. So what should we do? We know what the Celsius curve looks like now. So what should we do? Because we're trying to find this right here. Standard deviation is 5, right? Or is it 7? Did I get it right? Standard deviation is 5. So what should we do? That's our answer right there in yellow. Does it make sense, Sarah, when I draw this out like this? That's a really tough, good question. Now that I see it, I'm like, man, draw. What do we say? We say it in class. We say in class, draw it out. Do you see? So what should I do, Sarah? What is 2 degrees Celsius to Fahrenheit?
That would be 35.6 degrees Fahrenheit.
What do you think I should find out next? What do you think I should find out next? So solve from here. Oh, we got some, looks like Canvas content. What do you think we should solve next? So we're almost there. We almost have our answer in yellow. Convert 7. What is 7 degrees Celsius to Fahrenheit?
The answer is 44.6 degrees Fahrenheit.
There we go right there. And you said the answer is, well, let me double check because these numbers, I'll show you these numbers. So standard deviation is 5 degrees Celsius. Are they seriously saying? Because it's the units of Celsius are not, well, it's 5 degrees Celsius. So it should be, because we're getting a 9 for standard deviation right here, right? So the standard deviation, if we go up 3 standard deviations. Was it, oh, my head was in the way? Yeah. Because of the way it works. I know, pain, right? It's such a weird problem. Politician stuff. Because that's where the number should be on that curve. And converting it to Fahrenheit, we're not going to get consistent distances, are we? It's going to be dividing the numbers, multiplying. It should be. You're saying that you said the answer is. You said the answer was what? You said pain. I love that. So the answer I'm getting right here is the standard deviation is 9. And does it like that? Because now the IQR, I know we got the range right. So now the IQR is going to be the range of the middle 50%. So the range of the middle 50%. So now I almost think they want you to go into a normal calculator. If you know that it's 9, the range of the middle 50% in Fahrenheit would be 9 times 0.674 times 2. 0.674. I'm going to be reviewing this problem times 2. Oh my gosh. 0.674 times 2 times 9. 12.1 right here. Type in an integer or a decimal. How many decimal places does it want on these? I'm a little worried on this one, Sarah. 83% correct. It's not even going to show me what I got correct. Let's look right here. Let's type in 7. No, that one was correct. We got 9 correct. So let me see. It's mad about the IQR one, I think. Yep, it's mad about IQR. So it didn't like the way I solved that with my quick solve right there. So it says the IQR is 18. So if the IQR is 18, that's the range of the middle 50%. So, okay, I see how they're going to solve that. Well, no, they wouldn't. If they want you to... Another wonderful question about the number of decimal places. Exactly, right? So the IQR, I almost think this is not solvable. Like, I wouldn't know this for certain. I'm going to go and eliminate this question after this because I do not think theoretically you can get this answer correct. Do they say it's symmetric? I don't think they say the distribution's symmetric because you'd have to assume, it doesn't say it's normal. It doesn't say it's symmetric because depending on where Q1 and Q3 are at, let me think. The IQR, would that be the same? Because the measure is spread. And we know the temperatures are 18 away. So what we probably need to do, here's what we need to do. I think we can solve it. Well, what we need to do is we want to take temperatures that are 18 away. Okay, I think I see the solve for this now. We want to take temperatures that are 18 away. This is a math question. And what should we do here? What should we do here? What should we do now? So this is the trick, Sarah, is to solve for test cases. What do you think we should do here now? What should we do? Because it didn't say normal, so I was wrong to use normal curve. What should we do here now? Because we actually just did it for the previous problem and it totally worked. So we want to do the same sort of thing like we did right here and do it right here. So what should we do? Exactly, just convert them. What is 20 degrees Celsius to Fahrenheit?
Here's an answer from encyclopedia.com.
What?
The formula for
What is 20 degrees Celsius to Fahrenheit?
that would be 68 degrees Fahrenheit.
What is 38 degrees Celsius to Fahrenheit?
That would be 100.4 degrees Fahrenheit.
Go, and that's our answer. So it is going to be 32.4. That's the answer right there. 32.4. Wow. There we go. Let's do a quicker solve of this. We're going to do it one more time right here. Let me reload the quiz. Question 12. Let's do a quick solve. I don't love the question. So long solve. Let's put long solve, quick solve. We'll talk over the theory right here and do it right. Why is it in the normal mode? I don't know. I'm talk to Terry. All right, stat 201. It's about converting units. It's more of a can you convert units problem. Okay, so here we go. Right here, we're going to do a quicker solve of this. And so people can watch a more edited version of this and quick solve a high school senior. Okay, so let's reload the question. Question 12 right here. Reloading that awesome question. And so here we go. So this question right here, with some of these, and as I was noticing as we were doing this, you can't just convert some of them because some of these are actual temperatures, but some of them are ranges of values. So when you're doing the maximum temperature, that is an actual temperature. Like that was the hottest day, which isn't actually that hot. So the hottest day, two sizes, you bet. So with the hottest day, we can just convert that temperature right there, 9 degrees Celsius, pull out your phone right here, and it'll do the math for you. You do just want to plug in the value right there. What is 9 degrees Celsius to Fahrenheit?
It's 48.2 degrees Fahrenheit.
So that would be an actual temperature during that day. Next, you have the mean, which is an actual temperature. Like you walked outside. Hey, Leo, good to see you here. We're practicing.
Notation, brother.
Good to see you, Leo. So it was negative 2 degrees Celsius on average. So that's an actual temperature. What is negative 2 degrees Celsius to Fahrenheit?
The answer is 28.4 degrees Fahrenheit.
Same with the median. So these are all positions and actual temperatures. Median's another thing. So that's 32, right? We can do that one. Just plug in. That turns out 0, 32. Classic right there. Now we get to the weird ones, the ranges. So the range might be the hardest one to solve for because when you're solving for the range, you see right here, it doesn't give you the range to begin with. Well, there's the range right there. So there's a range. Nice and easy. So let's go ahead right here and probably the quickest solve. We're doing quicker solves right here. So if we want to do the range, which is 28, we should go and take Celsius temperatures right here and figure out a hypothetical range. So we know the range is 28. Awesome. Oh, even Professor Moon agreed. Dr. Mark Moon is absolutely awesome. I appreciate that. Shouts to Mark Moon. He says, cheating is so fifth grade or something like that. He has a saying, cheating is so high school or so middle school. But Mark Moon is absolutely awesome. Shouts to Mark Moon. He should get so eighth grade. Cheating is so eighth grade. Tell him we have that as a quote in here somewhere. It's quote number something, but cheating is so eighth grade. Mark Moon quote right there. Huge shout outs to Mark Moon. I don't know. I can't search the quotes, but I wish I could find it. So we know 32 degrees. This might be the easiest way to solve stuff. In Fahrenheit is 32 degrees or 0 Celsius. What is 28 degrees Celsius to Fahrenheit? Boom. The range is what? Nice and easy solve. Where the range was 28 before, we got a quick and easy solve right here on this. So that should be correct right there. I think that should work. Little worried because we know what the maximum is. So maybe let's double check our answer right here. We got an answer of 36. We're going to do a double check right here on this answer because we know what the max is. So maybe let's use our actual max, which is 9. So if we know that this is 9 and the range is 28, then the minimum would be negative 19 because that's the range is 28. So now we want to know on the Fahrenheit scale down here. So what is negative 19 Celsius to Fahrenheit?
That would be minus 2.2 degrees Fahrenheit.
What is 9 degrees Celsius to Fahrenheit?
It's 48.2 degrees Fahrenheit.
And that is not the same. So we need to use the values in the context they have. So we need to make sure, and that makes me worried about the last one right here, but we need to use these values in the context they have because we know right here, the values right here, the min and the max, using the range right here, we can get from the max to the min, and then we can solve for the Fahrenheit scale, and we can get the range right here, which is going to be 50.4. We need to add those numbers. So the range is going to be 50.4, a little bit of a tougher one to solve right there. For the standard deviation right here, we know what the mean is and we know what the standard deviation is. So let's go ahead and plug in similar numbers right here. We're just going to draw the normal curve this time to do it. And so we know the mean is -2 and the standard deviation right here is going to be -7 rather, if we're going down, and this would be -9. So let's convert this Fahrenheit right here, or Celsius to Fahrenheit. And so what is -2 Celsius to Fahrenheit?
That would be 28.4 degrees Fahrenheit.
What is -9 to Fahrenheit?
15.8 degrees Fahrenheit.
And the answer is going to be the distance those numbers are away. So that is going to be the solve right there. 28.4 minus 15.8, 12.6. 12.6. Now, last but not least, the IQR. So the IQR is the range of the middle 50% right here. So last time we solved it and we got it right by doing our own range of values right here. It was 18 last time. We did 20 to 38, which was just some random numbers we picked, and it worked out because it gave us the right. Let me see right here. What is 18 degrees Celsius to Fahrenheit?
The answer is 64.4.
You don't want to do that because that would be finding where 18 is at. You want to find the distance two numbers are away. So we're going to do the same sort of work right here where the IQR is 15. That tells us the distance these two numbers are away right here. So the distance these two numbers are away would be 15. And since we know there's a distance of 15, we have to figure out the distance two numbers on the Fahrenheit scale would be away if they're a distance of 15 away. What is 20 degrees Celsius to Fahrenheit?
68 degrees Fahrenheit.
What is 35 degrees Celsius to Fahrenheit?
95 degrees Fahrenheit.
And there's our answer right there, is the difference between the two numbers, which is going to be 27. Definitely a longer problem to solve. Way too much math. No more math. Woo! Well, that's... So, Sarah, really good question right there. Much longer to solve. Me solving this as quickly as I could, even talking through the theory, it still took 6-7 minutes to solve. So it's quite the problem. Doesn't really cover normal model a lot. Yeah, it's a bunch of conversion stuff. I'm gonna take a picture of it and mark this question. We added a lot of questions this semester, and I'm not a huge fan of that because it doesn't really talk about normal model much. Not a big fan. What is the next question we have on the list? We have the Canvas content. So people wondering about Canvas content number 2. Let's go take a look at that. Chapter 3 and 4. So let's go look at that right here. Oof, good question, Sarah. Do you have another one? A study was conducted about shoe sizes. So a study was conducted about shoe sizes. We'll do that one next year, Sarah. Thank you so much. Stat 201, Chapter 5, Quiz, Part 1. A study was conducted about shoe sizes. Just here in a little bit. Let's do a little Canvas content. Do one version of it, then hop back here to the quiz. And definitely check out, we've done a lot of these during office hours, so check out some other office hours. We're going to do one version, and what we get, we get. So check out the version we're about to do. But remember, if I don't do the question you're wondering about right now, then what should you do? If you don't see the one you're wondering about, what can you do? If you don't see the question you are wondering about, what could you do? Head over here to the main screen. Okay, we're doing one version of Canvas content right now. So if you don't see the one you're wondering about, check out some of the more recent office hours from last week, and we might have done the question you're wondering about or talked about it. We're going to talk all the theory here for each question we do. Box plots, plural, are not ideal for comparing multiple groups. Box plots, plural. Box plots, plural. Just so you can see what we're talking about here, it says box plots are not ideal for comparing multiple groups. What do you think about that? Box plots, plural, are not ideal for comparing multiple groups. Box plots are not ideal for comparing multiple groups. What do you see right here? False, because these are box plots up top right here comparing, and we can make this nice and pretty. Give me 2 seconds. This is one of my favorite packages right here. GG Pub R. Watch this. We're gonna make some really pretty box plots really quick right here. So we just grab this right here. We drop the name of the data frame. We drop the name of the variables. We're doing, I think gender goes right there. I'm gonna reverse it. Color by gender, yes. Then we go right here. We remove out one of the colors. And we should be good. Oh, error stringed false. Is gender a string? Oh my gosh. 2 seconds. Class of survey 10 gender. It's a factor. Well, then why doesn't it like that? What did it not like? Error, can't find the name dose. Oh, I left a dose in. Haha. There we go. There you go. We'll put jitter. We won't add a jitter to it. There we go. There you go. There's side-by-side box plots comparing multiple groups using one of the packages that's really awesome. And I do love this because you can actually turn these into interactive graphics. So if you're ever wondering about any of this kind of stuff, let me know, because this is a really great skill set to have, is to be able to make stuff like this, that you now have interactive graphics right here that you can even remove stuff and remove out groups. So these graphics can be put on the web. You can even like zoom in on them, and a little bit of work, and we can compare things and see the 5-number summary and even highlight over and see outliers. So really kind of neat right here. You get the 5-number summary. You can tell the range is 18. You can tell the IQR is 4 because there's Q1 and there's Q3. And that's why I love doing this kind of stuff right here. We could add titles and all this good stuff to it, but I'm not going to focus so much. But we do see this is false. Box plots, which are going to display for us a quantitative Y value and a categorical X, are ideal. And that's box plots, plural, not a singular box plot. That's one box plot, which shows the 5-number summary, but multiple box plots are going to be excellent for comparing multiple groups. So that's false. There is sometimes a good reason to remove outliers. True or false? Sometimes we can remove an outlier. You can sometimes remove an outlier. Here, watch this. Would you remove, so I want you to look at this data, and I know this is a different program, but would you remove an outlier in this data set now? Would you remove an outlier? Yes, no, and why? Remember, we're analyzing height right here. Would you remove an outlier in this data set? We're analyzing height. Would you remove an outlier? So if you look, the female distribution has an outlier down here. Would you remove this outlier? Yes, no, and why? We're analyzing height. So we always want a case, like an example of, would we do this? Would you remove that outlier? Yes or no, and why? There's an outlier down there. Would you remove that? Yes, no, and why? Remember, we're analyzing height. So would you remove that outlier? There's sometimes a good reason to remove outliers. Would you remove it? Would you? And why? What would you give as justification if you did it? Who's got what would you say? Remember, we're analyzing height. So what does this mean down here? What does that mean? These are heights of individuals. I'll turn the jitter on so you can see there's multiple individuals that are kind of outliers. So the jitter is where it just moves the points a little bit. So if we go jitter right here, can it do the jitter on that? Oh yeah. Oh my gosh, it's a little crazy. There's a lot of points right there, so we don't want to probably have the jitter back on, but there's a lot of points. But would you remove that point? What does this point mean? Who knows? 1,000 points in the chat. Would you remove that point and why? We're analyzing height. These are the heights of individuals. Would you remove this point right here in the data and why? Or why not? What are people's thoughts? Give it a second more. But if you answer this question, you know the answer to the question on the Canvas content. Because this point down here is a person who reported having a height of 0. That's an individual who said, my height is 0. Well, you can't have a height of 0. Now, we're not saying when we would remove outliers at like a certain point. We're not being like, oh, if you have a height below this, we'd remove you. It's a little hard to say when we remove stuff because that's a little subjective. But there is sometimes a good reason to remove outliers, like when the information just can't be true. We could try and correct it. We could try to fix it. We could go back to the original data. But sometimes, in instances, it's sometimes a good reason to remove outliers, or sometimes you have reason. Below is a contingency table of students by if they were born in Tennessee and whether they are an honor student. What is the probability of a student born in Tennessee being an honor student? So I need your help on this. Who is here? We need help on this. How many students were born in Tennessee? How many students were born in Tennessee? So how many students were born in Tennessee? I need your help on this. How many students were born in Tennessee? So looking at the data on the screen, let's first figure out how many students were born in Tennessee. So what do people think? I might do an alternative solve. So if you're here and can help out, I might do an alternative question. So if you're here, help out with it. So let's do an alternative version of this because we need to know how to do this for the test. Alternative version of the honor students. What percent are born in TN? Of the honor students, what percent are born in Tennessee? Of the honor students, what percent? And so we've done this problem before. So I'm doing an alternative solve of this. So we need to know how to answer questions like this. And when we say of the honor students or what percent of Tennessee students, we're asking about a conditional distribution. So of the honor students, what percent are born in Tennessee? Well, then we're asking within the honor students, what percent are born in Tennessee? So that would be the answer there, 5 out of 65. So if the question were worded this way, this is an alternative version of a question. We need to know how to solve other types of questions, not just the one we're presented, but alternative versions so that way we're good on the test, because this is a conditional distribution, like your question over here is conditional. What percent of the Tennessee students are honor students? So it's only Tennessee students. What is the probability of someone being a Tennessee student? Just like the previous question, we can do an alternative solve of this one right here. And so when we think about this, we have two marginal distributions. Marginal distributions are the distributions in the margins. This is the marginal distribution of honor students. So what percent of students are honor students is going to be this. That's the percent of students that are honor students, 65 over 923. What percent of students are not honor students would be this. And these are all marginals because they're in the margins of the distribution. Over here, we have the marginal distribution of born in Tennessee. So we have what percent of students are born in Tennessee is the math right there, 574 over 923. And also what percent of students are not born in Tennessee would be the math right there, 349 over 923. Those are the marginal distributions. Last but not least, we have a contingency table showing whether or not people like chocolate and what flavor it was given to them. So this one has a lot of different ways it could go, because who here, tell me if you can answer this, if we were to say, of the dark chocolate people, what percent of them dislike their chocolate? See if you can answer this. I might need to reload chat. I'm going to reload chat. Maybe chat's stalled out here. So let's see right here. There's class. So of the dark chocolate, what percent of them, of the dark chocolate, what percent of them disliked their chocolate? So of the dark chocolate, what percent of them disliked? See if you can get this. Of the dark chocolate, what percent disliked the chocolate? Of the people who rated dark chocolate, what percent disliked it? So could you do that right there? Of the dark chocolate, what percent disliked it? How would you solve this? Knowing how to identify a conditional distribution is important. So, of the dark chocolate, what percent of them disliked it? So, when we say of, we're talking about conditional, or for those who tried dark chocolate, there's many ways to say it. For those who tried dark chocolate, of the people who had dark chocolate, Jackson, great job right there. Jackson, we said 1,000 points. Yep, that's going to be right there. And so that's got the answer right there, Jackson. That's how we would do it. We'd say of the people who tried dark chocolate, there were 98 who disliked it and 200 total who tried it. So it all depends on what we're asking when we look at this. Can you tell me, Jackson, what percent of people tried dark chocolate? What percent of people tried dark chocolate? So if we said, what percent of people and where would you look for this? We're just understanding how to read this table and do marginal and conditional distributions because we need to understand any question that could be asked. Jackson, you're on a roll right there. You got it. So if we were to look at this, and there's the dark chocolate right there, and this is the marginal. So it's just that information right there. It's only the 200 over 999. So let's look at the question we had on this one, and it says, what percent were neutral about the chocolate they tasted? So what would we do right here, Jackson? What percent were neutral about the chocolate they tasted? This is a marginal distribution too. Notice it says nothing about their rating. It just says what percent were neutral about the chocolate they tasted. That's it. Yeah. And hopefully with the practice, it just gets easier to do these to be like, oh, that's a marginal. So we just look at the margin right there, 229 divided by 922 or 992. Got it right there. Jackson, great job. Excellent work. Good practice. Just try getting it down, answer all the questions. Because once you see marginal and conditional a whole bunch of times, you're like, oh, that's a conditional display, which just sets a condition for one of the variables and looks within the distribution of the other variable. Let's see right here. Let's check out the last question of the day. Looks to be a study was conducted. Where's that study? Ooh, that's some pretty curves right there. A study was conducted. A study looked at. No. We're looking for study conducted. Little chill music right here. They really care about steer weights. Study was conducted. It's gotta be, there we go. Study was conducted. What's more, conversion to units. Okay. A study was conducted on shoe size. Let's take a note right here where we're at. And 124, 125.03. Study was conducted on shoe size of students reported in European sizes for the men. The mean was 43.79. Standard deviation was 2.26. To convert European shoe sizes to US sizes for men, use the equation below. What is the mean? Okay, so this is going to be very similar to the last problem we did where we were doing the conversion from Celsius to Fahrenheit. So we're going to use the same sort of theory right here. So the mean is just going to be a simple conversion because the mean is saying like, we have here, the mean was 43.79. So let's just take and run it through the formula. We're going to euro size right there. 43.79 times 0.7958. We're just putting in the mean right here. And then subtract off 23.6. So 11.24. That's the average male shoe size? Sure. 2 decimals, 11.25. Sounds about right. Shoe sizes in America for men range between 0 to 16. But that's apparently the mean according to this. Now, when it comes to the standard deviation, what we want to do is we want to take the values right here and we want to put them on the scale and actually find it. So this is very similar to the last problems we were doing. And let's go in here and do this. Okay. So we have Europe and we have American. And the European scale is going to have 43.79 at the center right there. And then one standard deviation up is going to be 43.79 plus 2.26, 46.05. And the American We already converted the mean. So that's from the previous solve. We just solved that a moment ago. Now we're just going to plug in 46 point. Plug in the, whoops, not there. I'm going to plug in 46.05 right there. And we're going to convert that to American units. And so now we go ahead and multiply this by 0.7958, subtract 23.6, 13.05. Oops. And that's a difference of 1.8, it looks like. Let me double check. So 13.05 minus 11.25, 1.8. Interesting problem. Interesting problem. Round to 2 decimals. Ooh, you better not be mad. Woo! Interesting problem. Good question, Sarah. A lot of those are on conversions, just showing you how we convert between units. So a lot of unit conversions. Are there a lot more of those? Definitely not my favorite problems. I love some z-score stuff. That's what the normal curve's all about. I mean, I guess we do convert between other units, but I'm all about those z-scores. All about those z-scores. A lot of problems. Do we have any other unit conversions? Shifting and scaling. Excellent. Good questions, Sarah. Those are the tougher ones, I'd say. So, he is, after examining a child, to pick up the pediatrician set the z-score. Country was 0.52. That means he's above the mean. Standard deviations above the mean. That's an easy one. Cool. Seeing what else we got in here now. Suppose your force is z-score. You got a 2.5. Right sentence, you were 2.5 standard deviations above the mean. And about what percent of the class scored higher than you? Type in integer. Well, that's your friend got a z-score of -2. Lower than your friend. So about 2.5. That's the empirical rule right there. About 2.5% scored lower than your friend. It's all about those z-scores. Sounds fun. We did this one earlier, so check out that one we did earlier. We got languages right here. Let's check this out. To qualify for language honors, a major must contain at least an average of 85. All languages taken so far. Which of the following do Anna and Megan qualify for? Let's look. 2 language majors, Anna and Megan took exams in 2 languages. Anna scored an 82 on both exams. Megan scored a 77 on the first and a 90 on the second exam. Overall, students on the first exam had a mean of this. Okay, standard deviation of this. So she was average on the first. She was 1.66 standard deviations below. And the second exam had a 73, so she was way above, but larger variation. To qualify for language honors, a major must maintain at least an 85 average across all language courses taken. So which of Anna and Megan qualify? So Anna scored 82. So Anna did not qualify. She had an 82 on both exams. Her average is not 85. 77 and 90 averages to right below. Ooh, 77 plus 90, 83. So neither of them qualify. Sorry. Who did perform better overall? Well, their z-scores are a bit interesting. So, no, I think, yeah, because Anna on the first exam, it's an interesting question. She's got 2 different distributions. Anna scored the mean on the first exam, so that's easy to compute because the first exam had a mean of 82. Megan on the first exam, so we get observation. Megan scored a 77. The mean was 82. The standard deviation was 3, a very small distribution. Megan scored lower. So Megan was below average on the first exam, but Anna was average. The second exam, right here, Anna scored a 82, and the mean on the second exam was 73, and that would give her a z-score of 0.6. So she scored a little bit above, where Megan scored a good bit above. So Megan scored a 90 on the second exam, and Megan, thus above the mean, was 17 points, but she is 1.133. So if you look at that, Megan was below the mean by 1.66 on the first exam. So if you average the 2 numbers, Megan was not, like she was a little bit above the mean and a little bit more below the mean, where Anna was the mean and then she was a little bit above. So Anna, performed average. That's a really, it's 2 different distributions. It's like, because, yeah. And let me write that down for you. The numbers we observed were the z-scores for Anna had z-scores of Here's exam 1, E1, E2. Anna had z-scores. We want Anna down here now. On exam 1, she was the mean, and on exam 2, she was a 0.6 standard deviations above the mean. Megan was negative 1.6 below for the first, and then above on the second, she was 1.13. So if you look, as we're saying right here, these are above the mean. That's directly the mean. These are below the mean. And Megan was below the mean by more on her first exam than she was above by the second. Pretty good problem. I wish they went more in depth and had you solve the z-scores. But overall, they should have you look at the z-scores right there to compare things, which is the whole point of looking at z-scores, is to compare different distributions, and you just have a lot more z-score calculations, which is the main point of this chapter, is to compare z-scores. So everything else is looking good. It's definitely those unit conversion problems that I don't think are really necessary, because we won't be doing that on the test. So I always like to teach the test to a certain extent. Every other problem looks good, but those 2 unit conversion problems are really not something we do a lot in this class on unit. That's much more of a math thing. Also, the biggest thing too is in practice, if you ever had a data set right here, like I think there's temperature data, right? So here we go. Is this in Fahrenheit? So like, let's just run this right here. R function convert Fahrenheit. So we just want to find an R function that does this for us. Be much easier. You know what I'm going to do? I'm going to end with this right here. Writing functions in R. Let's end with a little 474. Okay, so we're introducing 201 and 474. So we'll end with this. So BS 474, writing a function to convert values. A little convergence between the classes. So we have right here temperatures that are in Fahrenheit. And we go right here and we take a look at them. And there's a bunch of Fahrenheit temperatures. So we know the formula to convert the values is going to be, is it 9/5? 9/5 times Fahrenheit value. Fahrenheit value. Good to see you here, Kayla. Minus 32, right? So we could check this by going here and storing into Fahrenheit value 100. And I forgot to do the multiply. Very common error. I'm not immune to it. And no, is it 5/9? I think it's 5/9. Nope. Good to see you here, Elena. What are you wondering about, Elena? I'm about to do some conversion of values right here, converging my 2 classes. And so Fahrenheit to Celsius is that. So we'd need to 5/9 minus 32, right? 5/9 minus 32. Because we're converting. Let's look up the formula. Formula. Convert Fahrenheit to C. Here it is right here. 32. So this is what we have for Fahrenheit temperature. There's the multiply. And there's the value. It's mad about, I think it's the minus is not the actual. Yep, there it is. So Fahrenheit of 100. Fahrenheit of 0. No, it's 32. We'll do it, right? There we go. 32 is 0. Good. Well, that would solve any which way. Just somebody say, oh, awesome. Thank you, Elena. So what we're going to do is we're going to make a formula right here that runs this for us. Or, frankly, we can just convert this whole vector of data because now we can just plug it in right there. And there's everything converted. So we don't even need to write a formula. Or we could. So we go right here. Let's say convert F to C. And then we write here fun. Delete off the extra stuff. I should just write fun to begin with. Slowly losing my mind. Fun. Convert F to C. Input vector. Return this. And there we go right there. Convert F to C. Convert F to C. Input Fahrenheit. Oh, there's our Fahrenheit value. Input this data right here. And now we've converted it. No. Oh, because I have this. It needs to be vector. There we go. And run it, and it does it. So this is kind of the goal right here, is being able to write and make functions especially in 474, being able to tailor make your own stuff, because now we don't need to do the work anymore. It'll just convert this data set for us. And that's kind of the goal of like writing functions, is to have the work done for you easier, quicker, more efficiently. And now we just have a function that does it. There's probably a function in R, I would think, that does it, but we made our own. And let's actually go in here and add a round around it. Add a round and put 2. And now when we convert it, oh no, where did I put the wrong thing? Oh, I have it around the return. There we go. So it goes there, and there we go. Whoa. Why? Oh, I know why. Because I think I have my digits. Options, digits equals 7. There we go. Oh, and the data set's interesting. It's like it's a time series object. So this is a time series object, class time series, yeah. Let's say time series. So you know what you can do? So you can go to plot.ts and you can get a time series plot just like that. And also, I bet you, library, TS box, this is why we like functions, TS to Tizble. And let's take this, turn it into a Tizble. There we go. And so now that we have as a Tizble, let's store it as Tizble object. And let's take our Tizble and auto-plot it. Auto-plot the Tizble. Oh, is it not correct? Oh, we can't. Let's see right here. Tizble. Pipe it into... Oh, what did I... How just run that? I did pipe it into auto-plot. Let's go to auto-plot. Oh, because we need the variable name. It's value. Okay. What is going on? Tizble's working. Auto-plot value. Why is my brain not working today? You code for too long, everything, your mind starts to go. Objects of type Tibble, but it should be a Tizble. Look at the class of this. Table TS, table time series. Tizble. It is. I thought it was a as.tizble. Oh, maybe. Okay, 2 seconds. There we go. I hadn't loaded my... it was the autoplot wasn't the proper autoplot function. There's 2 autoplot functions? It's in the feasts. So apparently, there's another autoplot function that was unhappy, but I was like, it's not making sense, so I need to load up FPP3. So what we could do right here now, so we can go to plus and go to GG title, or let's go plus labs. Go to title equal my title. There we go. Go to library, GG easy, and then add to this an easy center title. And there we goes that. More title. There we go. And then let's go right here and load up library. And I want to show why I'm doing this. Because every time I load a library, I get more functions. Like these themes right here are just extra functions right there, like theme classic. There's just different themes I can do really quickly by choosing a theme and adding it on here. And I probably want to go and add my center title. Oh, that centers the title anyways. But I probably want to center the title after adding the theme in case we want to do it in that order so we get the thing back and centered there. But these are all just easy functions right here that you can run to change the look of your plot. And we can get some pretty decent looking plots right here. Let's go to pub clean. That's interesting. But all this stuff right here. Now I wonder what would happen if I take my object and go to my ggplotly, which is going to turn it into a plotly object. And oh, there, wait. Is that not the right plotly object? Oh, it didn't store something. Let's look at graphic P again. And nope, we didn't run this. So, okay, that should have stored into graphic P. There it is. Now let's ggplotly it. There we go. So now we get the interactive plot once again using Plotly. And this is just kind of a talk on functions right here to end. So the idea of being able to write functions is something very important because all a function is a set amount of code. So we wrote a function over here that ran this set code for us, but all these libraries I kept loading in have my additional functions. So I need my function that converts a time series object to a Tizble. Then I need my function right here that is going to autoplot, and autoplot is inside of the feast library. So that's a function that does the autoplotting for us. Then I have a function that adds labels to it. So I could add my y and my x label. If I just want to call this like y equals new y label, we can do this right here. We can take a look. Oh, no comma right there. So I didn't add a comma for my argument. But you can just keep kind of adding things right here. New y label if you want to add a new x label. And just having practice of doing this is super important. New x label right there. Well, that's got it. Excellent work today, everyone. We'll be doing more work tomorrow. But until then, bye for now, everyone. Bye.